introduce the speaker?
Good.
Would you introduce the speaker, sir?
Oh, yeah. Hey, good morning, everyone. Thank you for coming. Today we have Dr. Pramanik from the University of South Alabama, and I will let him introduce the topic of this presentation.
Thank you for the introduction. I want to thank Dr. Longla to organize this meeting. And I also want to thank Matthias for touring around different parts of the campus. And I also thank the whole department for giving me the So that might be the dependent variable. And then he wants to know that is it possible?
It is measured in particular region. So that means there is some error. Like if that person is very close to that particular region, so then it is a good estimate. But that person lives far apart from that region. So probably the incidence of the influence of the pollutant, we cannot measure properly. So that is why that is an issue. So in order to tackle those things, we construct this type of approach. Oh, it is right. So this is the total construction. So today's lecture is going to be these are the subparts of this thing. Yeah, so it is. So it is the subpart of this thing. So introduction, so motivation, what actually made me to do this type of work. So some background of the control theory, the dynamics. So we are going to use the dynamics of X. It follows some like stochastic Berson error, some assumptions, and the problem, the construction of the problem, and some quantum approach because I am using Feynman path integral approach. And there are some features of the trajectory, main proposition, and the discussion and future research. What we are going to do. So functional data analysis deals with the analysis of the theory of the data that has certain kind of functional form. So like in the regular regression, we have the dependent variable y and the independent variable x. Now, x is also certain function of certain thing. So usually in terms of statistical literature, this S is for some space, that is the region, right? Because at different point of the region, you are actually measuring certain value of the pollutant, like this example I was giving. But for my case, S is the time and T is the space. It is very weird looking because again, for my background of the stochastic control, usually the time interval is between 0 to T. And then when you put the integral, then it is for S. And then if you put the sub interval, then it becomes new. So that's the main issue for me. For my case, S is the time and T is the space, the region. So these are the three types of construction of the functional regression. One is scalar or function. So you can see the y is a scalar and x is a function of s. So this is one type of thing. Second is function on scalar. So you can see, so this is function and this is scalar, right? And last part is the function on function. So this is the part we are considering in our case. And again, the big issue for the third part is because this beta TS, like the Potier Kokoska, he actually defined this thing, it is an effect function and it is a kernel. And the big issue for this thing, it is infinite dimensional. That's why to deal with this infinite dimensional kernel, you need to have some further assumptions. Otherwise, we cannot solve the appropriate value of these betas. So this is the construction. So alpha S, so this is a non-stochastic intercept. Beta J, so in this model, I am assuming beta J is some kind of stochastic control. This is the control variable. Xij, this is the state variable in this case. And Ui, it is the error term. And again, space, this T, it is coming from the functional space. So that's why T is a subset, T belongs to tau X. And S is between 0 to T, that is the time. So that's why Xijts is an unobserved true functional predictor, so that this is the construction of the Bergson error. So the difference between the Bergson error and the classical error is, so for Bergson error, this is unobservable. So that is the we are talking about, like what exact pollutant that patient was exposed to, that we do not know. But we have some value from certain regions, right? Because at certain point of city, they can actually measure the incidence or the incidence of the carbon monoxide or carbon dioxide, right? But if that person doesn't live over there, so we cannot. So that means this is the true value, this is the observed value, and this is the error. Contrarily, for the classical error, we usually put this observed value is over here, and then the unobserved value is over here, and then we have some error. That means for classical error, so X, IJC, it is stochastic because it is depending on some unobserved X and some error term. So this thing is still it is stochastic because we have also some error term over here on the right hand side. But why did I choose the Bergson error? But again, you can use classical error. It doesn't matter actually, because we are actually trying to understand to find out the optimal beta J. That is our control. So these are the problems regarding these things. Since beta J's are infinite dimensional objects, which must be estimated from finite sample. So that's why perfect it is not possible without any further assumptions. So the popular thing is the restrictions such as smoothing conditions. So we usually use like Bayesian cubic smoothing splines. So different type of smoothings we usually do, and some penalization. So like the lasso, group lasso, bridge lasso, those type of penalization. And the most popular thing is the functional principal component analysis. So because this type of approach, they use some kind of wavelet equation, and they use the eigenvalue and eigenfunction. So that actually helps to reduce the dimension of this beta J. But my approach is, I am using the path integral control. What we are doing, the xj you saw, I assume that xj follows some stochastic differential equation, right? So, and again, I am using some path integral control approach. So these are the construction. When you construct a control problem, the stochastic control problem, these are the things we need to use. So what is a control theory? Control theory, it is a mathematical description of how to act optimally to gain future rewards. Because that's the thing we do. I work for university because I get paid. This type of thing. So again, historically, it is also true. Like if you give some award, that is actually gives some incentive for you to work in the future. I think this thing has been rigorously studied by Hilbert Kappen by Redbound University, and then E. Theodorou, now currently he is in Georgia Tech, and Fleming. So he actually first come up with this control theory, the stochastic, the path integral control idea. So the components of a control problem is first is the objective function. So in terms of economics point of view, you can think about the cost function or the profit function. When it is profit function, you have to maximize the profit function. When it is cost function, you have to reduce the cost function. In terms of statistical point of view, we have different type of loss function. Loss function is equivalent to the cost function, and we always try to minimize the loss function. And for our case, it is the residual sum of square or the mean square error. That is our loss function. We want to reduce, we want to minimize these things. So that's our objective function. So time, because we are considering the evaluation of the state variable over the time and also for the control. So that's why time is also an important factor. State variable, in our case, is the state variable is the xij, ts, that is our state variable. So state variable actually talks about like the true effect of certain components. Like in terms of economics point of view, you can think about the share at different point of time, like S&P 500 index, so Dow Jones. So those are the index at different point of time. Those are the state variable. And what are the control? Control is like, suppose you are an entrepreneur. So then how much you want to spend in commercial to get some profitability in the future. So that is the control. So you can think about like, suppose today you spend a lot of money in commercial, so probably you hire a celebrity, and then suppose you hire Brad Pitt and he is holding a perfume of your brand. So then people watching this thing is feeling that if I buy that perfume, so then probably I'll be like that celebrity. So that actually induces people to buy those type of products. On the other hand, if currently, if I am able to sell more product, that means what? In the next time period, I have much more time, much more money to invest in the commercial. So it is some kind of closed loop kind of stuff, the feedback. So we are going to consider a closed loop type of control because it is circulated. And the control variable, we talked about it. So it is the how much money you want to spend. And for us, it is the beta J, that is our control variable. Equation of motion, that is the stochastic differential equation we're talking about. So objective functional, it is a mapping from the control trajectory to the points to the real line. That is the definition of this objective function. So types of objective function we usually use of stochastic differential equation. So first one is the regular dynamic. It is called the Lagrangian problem. So how does it look like? So you have an initial condition and you have some objective function and you do not have any terminal condition. That is called the Lagrangian. Dynamic with terminal condition, that is called the Bolzer's problem. That is actually the popular practice. And in stochastic control, you have some initial condition, you have some terminal condition, and you have some objective function. And the last is, it is least used, that is the Myers problem. So Myers problem is, we do not consider about the initial condition and the objective function, we only consider about the terminal condition, right? So our case, as it is a forward-looking, we are going through a forward-looking approach, I am considering the Lagrangian problem. So these are the two main types of control. Closed loop type of control I talked about, like the commercials and these things. So and open loop control. So let me give you some analogy for open loop and closed loop. So open loop is like so when you dry your clothes, so you put a timer, right? So when the time is up, everything stops. So it is open loop. So it is predetermined. The policymaker actually predetermined when to stop the control. But for closed loop, you can think about the thermostat of the room. So you set a temperature. So initially the room temperature is lower. So it increases because the thermostat is on. When it hits that temperature you set, it stops. Then the room temperature slows down. Again, if it slows down enough, so then the thermostat is being on. So that's why it is closed loop. So it is the same thing for the commercials, right? So today I have enough money. I spend a lot of money in the commercial. So that means in the next time period, I have more audience. So that means I have more customer base. So then if I have more customer base, I have more money. Then in the next time period, I have more money to hire much more bigger celebrity, right? So this is the way it goes. So a dynamic mean square error over a finite time horizon has been minimized with respect to this xij, that is our state variable. So the important assumptions for this thing for the infinite time horizon. So I do not know how to deal with this when it is infinite. When it is finite, so path integral works. So what I usually do, so the time interval, it is from 0 to t. I subdivide into small subintervals, small equal length subintervals, and in those subinterval, I use the Euclidean path integral because it is actually the Feynman action. So you have to do some weak rotation. So then it comes from the complex field to the real line. So then life becomes much more easier because the issue of the Feynman path integral is it is not measurable. That was one of the biggest issue. But again, Feynman says quantum field work on this. So who cares about this thing? But later, I think in 2017, I think Daisuke Fujihara, he wrote a book about the measurability of the path integral, and he tried to understand rigorously the measurability of this thing. So what did he do? In this small integral, in this small time interval, he fit a Riemann integral, and then just do the regular thing. So we used an Euclidean path integral method to determine the optimal beta j, that is our optimal control. This is our mean square error. So again, this is the observed value. So this is non-stochastic intercept term. This is your dependent variable, and this is your independent variable. Again, it is also stochastic. It has the evaluation of a Brownian motion. So these are the structure, the stochastic differential equation structure of this XC. So mu is the drift part, sigma 1, it is the diffusion part of this XC, and V1 is the Brownian motion. And V is the Parson error. And again, when it is certain kind of error, always we know the mean of the error is 0. So that's why there is no drift part. Only we have the diffusion part with this second set of Brownian motion. And then this sigma 1s, this beta s, it is this kind of structure. So this sigma, it comes from the original Parson error. So can you remember, like when we started the definition, it was what? Xij equal to Xijc plus Vij. So sigma, that is the what? That is the variance of that Vij in terms of cross-sectional thing. And then you have this part, right? This is over the time, the evolution over the time. And then that sigma u, that is when we started our regression, what we had the Yij equal to alpha, right? That was the non-stochastic term. Then we have this integration plus we have some error term, q. So that is the variance of that u. And what are the assumptions? That u, it is independent to xij's and vij, and vij also independent to xij and uij. So that means we have some kind of orthogonality assumption. And again, you have some background probabilistic structure. So this is the sample space, this is the sigma algebra, this is the filtration starting at time 0 with respect to the state variable x, and t is the probability measure.
Could there be a sigma squared on the left side or something?
No, this is the standard
the
deviation.
right side. But the right side is.
So that's why it is actually the square. So that's why I need the transpose of this thing. Yeah, it is actually the square.
But on the left side.
Left side. Yeah, you are actually right. So yeah, that will be the sigma square. Yeah. So then this is the standard deviation. So yes, you are absolutely right. Yeah. So yeah, there should be, because that is the variance we are talking about. Yeah. So these are the popular approach of different type of control problem. So first one is the Hamiltonian approach. So this is very, very old. So when I was an undergrad in econ, I started this thing. So the Hamiltonian approach. So there are two types of Hamiltonian. One is called the current value Hamiltonian, and another is called the present value Hamiltonian. So the main difference between these two is current value Hamiltonian is like you have the objective function plus lambda is a function of s, that is called the co-state variable, times the functional form of the stochastic differential equation. So that means like in our case, we had what? dx equal to some mu ds plus sigma dbs, right? So the functional form is going to be dx minus mu ds minus sigma dbs. So that is the functional form of the stochastic differential equation. And then we are multiplying this thing with the co-state variable plus the objective function. And the present value Hamiltonian is like, so you have the regular objective function, you are multiplying by some discount factor. That is the main difference. Otherwise, everything are the same. Then what do? They solve for the system of equations. So we have the first order conditions. So for minimization or maximization, it has to be 0. But if it is not equal, so then we have to use some kind of Kuhn-Tucker condition, right? So then they solve for x, the co-state variable, and then from those system of equations, you can actually solve for the control, right? The second one, this is very, very popular. It comes after the name of Richard Bellman. So the big issue of Bellman equation is, so Bellman equation is what? First, you have to, from the objective function, you have to construct a very difficult value function. So then based on the value function, so you have to construct a partial differential equation. This is a partial differential equation approach. So the main issue for Bellman equation is, so if the stochastic differential equation is linear, so everything is very, very good. You have some unique solution. So the worst part comes like when it is nonlinear, like the Martin-Garman Hamiltonian type of equation, or like when the state variable is infinite dimensional. It is very, very hard to find some kind of Hamiltonian Jacobi-Bellman structure by doing the simulation. So that is one of the big issue. So what happens, like the path integral actually bypasses this approach and gives some different set of solutions. So what Bellman cannot actually tackle, because this type of concern was first introduced by Belal Bach. And then I think Theodorou, he actually said like, so it is because they are from computer science, they said like it is impossible to construct a Bellman equation when the dimension of x is very, very high. So the another approach, it is Lagrangian approach. It was done by Gregory Chow by University of Chicago, and it is very, very similar to the Hamiltonian approach. So instead of using the co-state variable, he used a Lagrangian multiplier and solved the same system. The Feynman path integral approach. So this thing was first introduced by Richard Feynman and then Marquardt. So what they did, like you have some stochastic differential equation with the value function, they construct a parabolic partial SD to find. But my approach is a little bit different because I originally stick to original Feynman's paper in order to find. So what did I do? I find a Schrodinger equation. From that, when you do the wake rotation, so you have what? Fokker-Planck diffusion equation. From the Fokker-Planck, if you differentiate this thing with respect to control, that is the optimal control we get. The last approach, it is the mean fit. It was developed by James Larcy and Pierre Lyon. This is very, very famous paper. And one of my complaint of this thing, like when they came up with this idea, so no big math journal accepted their paper. It got published in Japanese Journal of Mathematics, and now it is a very, very big thing. So Pierre Lyon, he got field medal in mathematics. So this paper is more than like 1,500 citation. And even like, so now he's a big name. So what happens, like he gave some lecture in college, the France. Somebody took the lecture, put it in archive. That thing has 2,000 citation. So even if you become famous, you do not need to publish, right? So mean field approach, so what does it do? It captures like when there are infinite number of firms in the industry. So they interact like a mean field in the physics. So what did he do? They do actually. So they construct a backward Hamiltonian Jacobi-Bellman. That is one system of equations, and the second is forward Fokker-Planck. So they solve these two systems at the same time and able to find out the optimal control. But the big issue, like, so it can capture like when the number of agents are infinite. But now current days, people have some questions about, so suppose the firms, total number of firms or total numbers of agents are very big, but not infinite. So how do you capture that type of scenarios? That is still an open question. People try to do. So then another type of differential equation has been evolved. It is called the Mackin-Vlasov type of equation. That is very popular these days. So these can actually tackle these type of issues. So my approach is what? So I use the original Feynman's paper, Journal of Physics. So we construct, first you have to define the action function. So what is the action function? Action function, I define the traditional present value Hamiltonian. That is my action function. So then what did I do? So from 0 to t, I subdivide this entire time interval into small time intervals. Then I feed Riemann integral in each of these things. And then we did a bunch of Taylor series expansion. So to find a Schrodinger equation, and then some wake rotation, then Fokker-Planck diffusion equation, and then differentiate with respect to the control, then we find out the data set. So this is the background assumption. It is some kind of Lipschitz condition. So again, we need to have some measurability. And again, we are using some linear stochastic differential equation. So that means to make the solution to be unique. So that's why we are assuming this type of thing. So, and this assumption is some background product probabilistic assumption. So it is just like we to make the solution exist and unique, some kind of stuff. But again, the issue comes like when it becomes like nonlinear stochastic differential equation, these assumptions doesn't hold. And in real life, these assumptions doesn't hold actually, because these stochastic differential equations, the solutions are not unique. Because if think about in the share market, if you have unique solution, so would you actually invest in the share market? No, you need some randomness, right? Otherwise, you cannot have more profit. If everything is predictable, so there is no profit, right? So that is the big issue. So then people usually use the Weinstein measure. So it is not like regular Ito or Stratonovich measure. So then it tackles, and then they try to find some mild solution, but the solution is not unique at all. So this is the main construction of the problem. So again, this part is the residual sum square. So these are the two sets of stochastic differential equation. So we are minimizing. So these with respect to alpha and beta, those are the controls in this kind of scenario. Right? And again, this expectation. So expectation of 0. So it is like forward-looking expectation. So that means it looks like that. So usually what happens, so when you do some subintervals at the beginning of any time period, we do not know what is happening at the future. So that is why our expectation is that for the time period is the expectation at the beginning of the time period, what we are observing. So that is the assumption we do throughout this thing. So these are the way of construction of my path integral that I was telling before. So we construct a Lagrangian function based on the dynamic mean square error function subject to the SD. We define a Feynman quantum action function based on that Lagrangian or Hamiltonian. So take a wake rotation of the Feynman action. So then define the transition function. In probability theory, it is nothing but the transition probability.
What is a wick rotation?
Weak rotation is like once you have like in action function in complex field, so then you have to like manipulate some kind of the time in such a way that the complex action function comes to the real, the Euclidean field. So that is the main difference. Because the issue for this thing is like when you deal with the Feynman action function in the complex field, the integration is impossible. It is not measurable. That was the big issue.
So it's a technical tool?
Yeah, it is a
for
technical
showing-
tool. Yeah.
for constructing things?
Yeah. So he was another physicist here. So he did that kind
Yeah,
of.
I know the name wick.
So that's why he did help us to find some kind of, because again, when it is a Euclidean field, life is much more easier than complex field. That's the situation. And again, so we construct the forward Fokker-Planck type of equation. So then we find the optimal cut. So this is the Lagrangian function we were talking about. So again, so this part again, it is with respect to time. So if you do not fit this thing with respect to time, then it becomes a penalization function, right? You are then you are integrating with respect to the whole area. but I am doing the local optimization. So that's why I also make this thing lambda. It is a function of time. And this is the action function we constructed. So the action function from 0 to t, where the state variable is xc. So it is the negative of the Lagrangian. So this is the construction. The big issue was this measure, the Feynman measure. It didn't exist. So that's why the weak rotation, I actually put those things in terms of Riemann measure. And again, that I was talking about, like, so I took the small intervals. So there are n numbers of small time intervals, and I fit like Riemann integral in small intervals, and then I try to do the action function in this. And these are the trajectories. Oh, again, this is some kind of like background understanding how we actually it looks like. So this is the initial state at time 0. What is the value of x naught? So these are the feasible conditions, and each of these are the movement of the state variable over the time. And again, we do not consider any type of terminal condition, so that's why we do not know how does it look like. But again, you can consider the terminal condition, then you can consider it is called the backward forward parabolic partial stochastic differential equation. And this is the construction. So after solving the Feynman action function, so that was originally our dynamics of x. So then we have the objective function is what? Mean square error. So we minimize the objective function subject to this thing, and at the background, we have the evaluation of the Barson error. So then if we use the Feynman action function, so then after doing the first order condition of the Schrodinger or the Fokker-Plumb diffusion equation is going to be this thing. And then if you solve for beta, so then you can find out the optimal beta. So now the big issue is, like, when you use the Ito's lemma, so we usually say if it is Ito integrable, there will be some C2 function exist at the background, right? So the big issue over here, so in order to make this thing, I assume this type of this type of C2 function, because the main issue is, again, if this is what some kind of integrating factor of the stochastic differential equation. So that is why that is the best bet. Even every time I saw, like when I use the Brent Oxendel's book, they always go for the integrating factor of the stochastic differential equation as the G function, the I function. Then, because the main issue of the Brownian motion is what? It is homeomorphic but not diffeomorphic. So that's the big issue. So that's why you have to do some kind of smoothing. So that's why we have to introduce some kind of C2 function in such a way that we do not deal with this kind of non-differentiability idea. And there are another approach, I think, Scott Sheffield, Jason Miller, they came up with the square root of 8/3 Liouville quantum gravity approach. They did the metric gluing. So that is also another approach you can actually do instead. So the beauty of this kind of approach is like, so they do some kind of square root of 8/3, and it is e to the power, and they have another function which is multiplied by 8/3. So it comes, the domain of that function comes from the complex field, but its range is on the real field. So that makes like much more easier, because again, it is e to the power. So that means what? It is smooth always. So then they did some kind of metric gluing in order to get rid of this type of surface. They call it what? The Brownian surface. That is the name of that. And as a standard statistician, I have to do some asymptotics. So that is the asymptotic. So theta is what? Theta is alpha and beta. And this type of asymptotics, we need to find certain kind of distribution of this theta. That is the variance covariance structure. So I use some result from Genling 1 and the book by Wellner and van der Wacht. So the empirical process theory. So because they have very, very similar approach, and Genling 1, she actually did estimate this theta by using some penalized regression method. So that's why the approach was very, very similar. So that's why I, from those two, not two articles, so one article and one book, I got this asymptotic theory of this thing. And the future thing is this method gives us a different set of controls than the Hamiltonian Jacobi Bellman. Because again, for Feynman, so what we are actually doing, we just minimize it. First we subdivide the time interval into small equal length time interval, and then we need to reduce this thing. So then in those local time intervals, we fit a linear equation because everything is locally Euclidean. So that is, we try to implement that approach. So that is why for certain case, when the SD is nonlinear, so the Bellman approach cannot give you the solution, but by Feynman is going to give you, bypasses this type of issues and give you some set of solutions. And again, are those unique? No, there are no unique solutions for this type. So continuous time is required to make this method to work. That is also very, very important assumptions for this thing, because nowadays people are interested in discrete time, right? So that this method cannot work in terms of discrete time. And this method can be used in statistical literature where penalization function becomes stochastic. So you can use the lasso bridge regression where you can think about the evaluation of this control is indeed following some stochastic differential equation. Right? And currently I am working with something again with the nonlinear SD like Mackin-Blasso, and where the objective function is mixed data analysis minus regression kind of stuff. Then we are trying to find the effect function on this. That's all about it. Okay. If you have any question, it was a small talk. It was not that long. Because the main issue for this type of papers is like there are not many theorems. The number of theorems are very small, but the proof of those theorems are very, very massive.
Very long.
Very, very long. Like for these things, this thing is what? Probably 26 pages. There are a lot of lemmas. And then, I think there is the paper is also with here. I think.
My comment is that my interest in this talk lies in the fact that my first PhD, that's in transpersonal control theory. And now that I think I have shown enough that I can do statistics, so these students might actually pick these topics to continue their research, and I'll be more than willing to continue working with the students on those. So it's a topic that is on program as well.
Because again, I don't think nobody did this type of stuff, because I see penalized regression, but I do not see anybody does use the state, the evaluation of the state is following some stochastic differential equation. So that thing I can say.
Questions?
So the problem is the construction of the mathematical construction of these objects is extremely heavy.
Yeah. Like heavy means like what?
Like what difficult? It's extremely difficult to know that solutions exist or to construct them.
So the issue is like, yeah, because like the beta, those are the infinite dimensional. That is also the big issue. Another issue is like the evaluation of this beta, like not the beta, the xj. That is also another important part, right? Because the construction is going to be very, very difficult when it is non-linear. Linear is comparatively easier, but again, to doing the Feynman path integral, it is also very difficult to. But so then some of the reviewers says like, so you did path integral, but it doesn't look like it is easier than the constructing the Bellman equation. But again, there are certain scenarios where you cannot use the Bellman equation, but you can use the path integral. So in terms, yes, it is heavy in terms of construction, but again, if you have the linear stochastic differential equation, and then if the x, the state variable, has very, very high dimension, so then you cannot do the computer simulation. But you will be able to find some analytic solution, but to make the computer simulation to work, it is impossible.
Awesome.
Yeah, I think Belalbach claims it is impossible. Yeah, I do not know.
Why not?
Because most of the papers I see, and also probability, they only do the analytic solution. I didn't see like Hugh and Pham, I think Amarjit Budhiraja, they work on this type of Bellman equation, but
One of the things that I remember is that the reason why most of the result at the time I was looking at it were not being used was that most of the theorems given solutions were in the form of the kernel that is abstract, so not really something concrete that can work. So you just prove that it exists, that the kernel has some good properties. We show that contracting up and that there's something involving the leaches.
this is the local continuity.
Yeah, leaches, and then conclude that the solution exists, but really you cannot show it.
So this type of.
It's still the same, people evolve because I haven't looked at it for.
Yeah, these are still open problems, like to do the computer simulations. And again, like in infectious disease modeling, this thing is also very popular. They call it SIR model, susceptibility, infection, and the recovery rate. So that is your state variable. That means what? You have 3 sets of state variables. And what is your control? The vaccination rate or the lockdown intensity. That is your control. That is the policymaker has the control, right? When to lock down the economy or how much vaccine you need. So that is
our control variable, then you can actually construct that similar problem. we're talking about. And what the objective function equals social cost. So if you open the economy, so what will be the social cost?
so.
We do have Chadrik and Dr. Dang online if they have questions.
I don't know if I can hear. So,
I'm good, Dr. Langland.
So C is the observed value of X.
I mean, so, at the beginning of first line, the notation, the boldface R, some I, right? But later you have a regular R,
Oh, okay, yeah.
the same,
So because again, it is the vector, so that's why I put the summation. This is just like one R. And this is the set of this, all
so
possible.
then over there, no I.
Oh, there should not be, yeah, that is.
No I.
Yes, that is.
And how about the last, the result, sigma I?
Sigma. Okay.
The variance,
Yeah, it is just going to be just regular.
that's the sigma.
Yeah, it's just like it.
And also the third line,
Third
line, there exists P,
in
the P over this square that's infinity with, what's the difference?
So the second part is the norm. And the first part is just like the regular differentiation.
Square arm?
Right, the second one is the Hilbert norm,
No.
L2 norm.
Is it a vector?
Which one? Yeah, second, yeah.
Second line is should be the.
So there should not be I in the second, yeah, I apologize to things. So yes, you are absolutely right, because again, this thing is the L2 norm. There should be the vector, but this is just for a single element. So that's why it is the I.
Yeah, you have OP. What P, you have to say if your P, when you convert to the CMFF, convert,
probability.
Yeah, convergence in probability.
but that with a little P over there.
The same.
The same P,
P of one.
OP one, and you have the same P with the P on the end over there.
Yeah.
But that with a little P on the downstairs.
So this thing is the convergence of probability and this is some rho.
That's wrong.
Yeah, this is the rho, yeah.
But that with a little P on the downstairs.
Yeah, that is different, yeah. Because we need to find some convergence of this, like the big O convergence with this lambda thing, because that is also the penalization function, right?
Thank you very much. We ending right on time, 9:50.
Dr. Virika, a question.
Really?
She admitted
I wrote and she didn't say she had a question. And Dr. Khan replies he didn't have a question. So regarding how do you know what you want?
We'll
Yeah,
just a chat. Okay.
I'm talking to them. Okay. She says she has a question. I don't see her message.
No, I'm good, Dr. Zhang.
No, she's.
Do you have a question, Saturika?
No, Dr. Longla, I'm good.
No, she's good, she says.
Thank you. All right.
Thank you so
We'll
much.
meet them next time. And I was hoping that next time it would be one of our students to end the seminar. This, I don't know which one, whether that could be Bartek or Hassan. Because Matthias and others have already showed so much. Yeah, well, I don't know. Would you be available? Or Hassan? Yeah, one of you two is, you are the only two that have something that they can show in 15 minutes.
So they have time to negotiate this.
Yeah. So you guys talk about it and let us know. That will be the last meeting of the seminar. So yes, in this academic year. Thank you very much.